Welcome to Toddcast number 47. Continue on with free radicals. Um, First one, we introduced free radicals. Last one, we went into free radical halogenation and left off with something known as selectivity. And so this was the graph we left off with last time. Again, want to emphasize that it probably is a bit lower for activation energy, but the key point here is that it still is a low activation energy with a lot of energy coming out of it, high activation energy with not so much energy coming out of it, meaning this is a very fast reaction. Chlorination happens very quickly. It is not very selective. It'll take pretty much the first thing it bumps into. Bromination, it will take the time to pick something right. So if it picks the wrong one, let's say it picks up an H and leaves a primary free radical, that primary free radical can now react with another molecule, maybe generate a secondary, tertiary, something more stable. So because it's very slow in its steps, it takes time to get a higher concentration, higher abundance of the more stable. Chlorination doesn't take that much time to be selective, so you end up getting more of a mess of a whole bunch of different products. So we'll look at what that means exactly. So let's consider this generic reaction where by equivalence, there's 1, 2, 3, 4, 5, 6 identical H's here. There's a plane in the middle. So 1, 2, 3, 4, 5, 6, meaning these 6 H's are all primary, and we have 2 secondary H's. So when X free radicals form, it can react and either abstract a primary, 6 choices, or a secondary. In doing so, the primary free radical, wherever it happens to go, can pick up an X, or the secondary can pick up an X, so you end up with only 2 possible products. 1 halopropane, so 1 chloropropane, 1 bromopropane, depending on what X I'm using, and 2 bromo or 2 chloropropane. So there's only 2 options, and so let's just consider what the standard run-of-the-mill probability would be based on how many we have. So I'm going to put a light blue circle around the secondary H's, a light yellow circle around the primaries. So you'll notice there are 1, 2, 3, 4, 5, 6 primaries, which means there's 6 ways to get this one. So no matter which H I take, it's still going to be 1 chloro, 1 bromo propane. So I have 6 possibilities for this product. And then there's only 2 secondaries. So 2 secondaries here and here, which means only 2 ways I can get this one. So if there was actually no preference whatsoever for primary or secondary, if it was all equally reacting, you would expect to get 25% and 75%. That is that 2 to 6 ratio. So if they both reacted equally, if primary and secondary were equally reactive, then 1 out of every 8 times would go here, 1 out of 8 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 here, which means 6 out of 8 times 75%, it would go to one of the primaries. And 2 out of 8, or 1/4, 25%, it would go to a secondary. Okay, it ends up, it doesn't do that. So let's look at the numbers and figure out what's going on here. So here's that same reaction. Here's propane reacting with Cl2. And rather than being 25 and 75% as just random probability would predict, we end up getting more secondary than expected and less primary than expected, which means it does in fact show some selectivity, some preference for secondary over primary. So what we can do mathematically is compare the ratio of 25 over 75 times some number equals 56 over 44, meaning there's some preference for the secondary over the primary. So this is going to be called the reactivity number. So the reactivity number is how much secondary is preferred over primary during chlorination. So 1/3 times what number equals a number around 1.26, 1.27. And so when you do that math, you come up with something slightly less than 4. So again, 2 secondaries, 25% secondary, 6 primary, 75%, equals times some number equals this. And so I'm going to call it the secondary to primary favorability ratio. So 2 over 6 is this part. S over P is this part, the secondary to primary reaction preference. and 56 over 44 is the observed distribution. So math is kicking in. So hopefully this makes sense. So again, we have 2 to 6 because there are 2 possible secondaries and 6 possible primaries. Secondary primary is some ratio of preference, and then the percentage we actually observe. Do the math, multiplied by 6, divided by 2 on each side, with 336 over 88, and as mentioned before, just under 4, which means the secondary is 3.82 times as reactive as primary. So it does prefer it. So when I said it isn't very selective, that's all relative statement, because 3.82 seems like a pretty good preference. Okay, we do the same reaction with bromine. We end up with 96 and 4, so we set up the same equation, 2 over 6 times the secondary over primary ratio equals 96 over 4. So 6 multiplied on top on both sides, divide by 2 on both sides, you end up with 96 times 6, so 576, divided by 2 times 4, 8. Dividing through, you'll notice this is going to be just under 75. So around 72. So bromine is in fact more selective. So when we say that it's more selective, it selects secondary 72% or 72 times more often than it'll select primary. Whereas for chlorine, it's only around 4 times it does it. So bromine is substantially more selective. So let's say you needed to get a primary alkyl halide. You'd want to do that reaction with chlorine rather than bromine because it's less selective, so it might give you more primary. And then you'd also want to do it at a higher temperature, because the higher temperature you are at, the faster the reaction goes. As a reaction goes faster, it becomes less selective, so you end up getting even more of that preference. So I'm going to specify the temperature for these numbers. Just took them out of the basically the information base had available. But note that if you raise the temperature, this preference starts going down and down and down. At a lower temperature, things go slower and they take time to be a little more selective. I'm not going to emphasize the different temperatures that much. Just want you to know that as the temperature goes up, you go faster and therefore less selective. The faster you go, less selective you are. Okay, so we've looked at secondary versus primary. Let's look at tertiary versus primary. So we have CH3, 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 and an H, so a T-butyl group. There is 1 tertiary and 1, 2, 3, 4, 5, 6, 7, 8, 9 primaries. So let me just emphasize that. There is only 1 H that can be lost to get that, 9. So again, 1 tertiary to 9 times the tertiary over primary selectivity rate equals 35 over 65. And so I'm solving for this preference. How much does it prefer tertiary over primary? So when I multiply by 9 on the side to solve for this, to multiply by 1, that's going to not matter. It's going to be around 315 over 65, which means it's going to be just barely under 5. So I'll get rid of my math. The math show up here. So again, 1 over 9 tertiary over primary equals 35, the tertiary product, over 65, the primary product. So 1 to 9 is the probability based on just how many there are, and T over P is the preference for tertiary over primary. So multiplying across, like I mentioned, 9 times 35 is 315 divided by 65, just barely less than 5. Okay, so it predicts or prefers tertiary by about a 5-to-1 ratio, secondary by about 4-to-1 ratio. I do not want you to memorize these numbers because they are temperature dependent. And if this shows up on an exam and suddenly they say it's only 3.4 and 4.2, you have to note that that is totally fair at a different temperature. So don't memorize these exactly because it's not, there is no exact condition. Temperature can change, conditions can change. Okay. For bromination, it was 72 for secondary over primary. So I know it's going to be in the hundreds, I'm assuming. It's going to be more preferable, but let's find out exactly how much. So again, the equation we're doing is 1 over 9, the abundance times the tertiary preference over primary preference equals 99.4 which is just absurd, over 0.6. So this number right here is going to be like 180-ish or so times another 9 is going to be in the ballpark of 1600 or so. This is going to be just extremely large. So we'll see where it ends up. So again, 1/9 times the T over P preference equals 99.4 for 0.6. 894 over 0.6. No, I said 1600, around 1500 or so. That is insane how much that prefers it. So bromination, highly selective by about 1500 for tertiary over primary and around 72 for secondary over primary. Chlorination, not very selective, about 4 and 5. Again, you don't have to memorize these numbers, but you do have to recognize chlorine is not very selective. Bromine is way more selective. So if you want to get a tertiary alkyl halide, use bromine, brominate it. If you want a primary, chlorinate it. You'll get a much better yield for those. That's kind of the take-home message I want you to have. So selectivity math, let's see it in action one more time. So here, I'm dealing with something that has a tertiary, secondary, and primary. So this has 1 tertiary. This has 3 primaries. It has 4 between these and 4 between these. So secondary has 4, secondary has 4. So we're going to have a slight sterics preference that I'm not going to worry about mathematically, but just something to consider. So when we do this, notice you get the following. You get the primary, that's this one here. You get the tertiary, that's this one here. You get the more sterically hindered secondary here, less sterically hindered secondary here. So I would predict 1 out of 12. So for tertiary, I would predict around 8.3%. That came out terrible. Let me rewrite that. I'd predict 1 out of 25 or 8.3%. I'd predict 25%. I would predict 33%. 33.3 actually. Let me be a little more precise. And 33.3%. That would be just straight probability for tertiary, primary, nearby secondary, far away secondary. The numbers I get. So let's see how this worked. 39, slightly more than expected. 39, slightly more. 7.8, 1/3 of what I expected. In fact, lower than 1/3 of what I expected. And this one, about 1.5, maybe 1.6 times as preferred. So these numbers, we'd have to do the same ratio as before. I have a 3-to-1 here. I'd expect 3 primaries to every 1 tertiary. So 3-to-1 times what, or I guess I should do it the same way. 1-to-3 times what factor would equal 13/8, so around 1.7. If you do that, it's going to be around 5. Same thing for primary compared to secondary, what you get. So the numbers are about what we saw before, about a 5-to-4-to-1 ratio. So it pretty much fits on the dot with what we just did in the previous example. So bromine, that means, is going to, if it's right, going to be about 1500 times 1, because there's only one of these. This is going to be 3, because there's 3 of them times 1 preference. And this is around 72 for each of these. So 72 times 4 will be 288 and 288. So again, what I did is I did 1, because there's one of these, times 1500 preference. I did 3 times 1, because there's 3 of them, but it's a preference of 1. And then I did 4 times 72 to get 288, 288. So whatever the percentages are, they should be in a ratio from this to this to this. So these should be about 5 times whatever percentages these are. These should be roughly the same percentages. These should be about 100 times what this is. So I'm going to just ignore this for a moment and say that this should be about 14-ish, 14-ish, and the remainder, so around 72-ish. So in the ballpark. And I should say that I didn't do my numbers exact because I made it roughly 300. So it works out fairly well. So the preference apparently was 1662 to 1. So I must have chosen a different temperature from the previous example, and the ratio isn't exactly what it was before, but it's in the ballpark. The numbers seem overwhelming, absolutely no doubt about it. It's one of those things that if you just simplify and say it's a probability, so it's a stat situation, the observed percentages of tertiary over primary, for instance, will equal the abundance, number of tertiaries, divided by the number of primaries in terms of sites, times this preference, whatever this number is right here. The math isn't that bad. So this is the number, and this is the percent tertiary formed over the percent primary formed equals the actual ratio, the abundance, times the reaction preference. Okay, overwhelming, I'm sure. Numbers are all over the screen. So what you're going to have to do is either from these numbers figure out these preference values, or given these preference values and observing the abundance on here, make a prediction of what percent distribution. It's definitely going to be weird at first, but if you do a few of these, it's not so bad. So bottom line, chlorination is less selective, bromination is more selective. As temperature goes up, selectivity goes down. So again, something I keep mentioning is if you want to get a primary alkyl halide, use chlorination at high temp. If you want to get tertiary, use bromination at low temp. When we get secondary, got to do a little more math, a little more figuring this thing out. That covers the math portion of this. This probably is going to be the hardest part of this chapter, the math. Once it clicks, it'll be easy, but make sure you know how to do it. In class, we'll go over it a little more slowly, but thanks for joining in, and I will see you at the next podcast. So stop recording now.